Welcome to Complex Analysis Lesson 11, Polynomial and Rational Functions. We'll define these functions. We're also going to look at a theorem concerning the factorization of a polynomial into linear and quadratic terms. We'll talk a little bit about Taylor series for polynomials, and then we'll finish with a representation of rational functions in terms of partial fractions. We'll give a couple of different ways of doing that and also an example. We saw from previous lectures that polynomials of a complex variable with complex coefficients are analytic everywhere in the complex plane. The quotient of two complex polynomials is what we call a rational function. We have an example shown here. And also from a theorem we had in the previous lesson, the quotient of two analytic functions is analytic except where the denominator is 0. So we see for our example here, at z equals 5 and z equals 2, this function f of z, this rational function f of z, it doesn't even exist, and of course is not analytic there. Just some terminology. So the denominator of this rational function is of degree 3. It's basically the highest power. And then the denominator is of degree 4. That's the highest power in the denominator. And these points here, z equals 5 and z equals 2, are known as either poles, or I think we called them singularities previously. Yeah, and the last point is, this is also something we proved previously, the polynomials, a complex polynomial can always be factored into simpler terms, actually into linear terms, where each one of the roots is exposed as a value in the factorization. And of course you can have repeated roots. What we're going to prove a little bit later in this lecture is that you can factor a complex polynomial into linear and quadratic parts, and there's some conditions on that, but we'll get to that in a minute. It's also possible to have something called a removable singularity. If you look at this rational function here, we first have it written out as an expanded form, and then when you factor it, you realize that you have a z minus 1 here and a z minus 1 to the cube in the denominator. And so technically you have a singularity at z equals 1, but you can take the limit of z equals 1. You can then cancel the z minus 1 in the denominator with one of the z minus 1s in the denominator, and then evaluate the limit. The top, of course, goes to 0. The bottom is 12. And the limit is 0. So we can redefine the function, or actually give it a value at z equals 1, the value 0, and that effectively removes the singularity. We'll see this in some more complicated functions, like, for example, the sine of z divided by z equals 0 is a singularity, but if you take the limit, you'll see that it does exist, and we can replace the undefined point. So that'll come actually several lectures later, but I thought I would mention it in a simple case here for rational functions. Earlier in a previous lecture, we had the lesson 4 actually, we had something called the fundamental theorem of algebra, and that said that if you have a complex polynomial with complex coefficients, you can factor it, as I've shown here, where the z1, z2, z sub n are roots of the polynomial, and that's always possible. What we're going to do in this slide is a theorem that's sort of related to this. Instead of having just a general complex polynomial, what we have here is a complex variable, but all the coefficients are real valued, and under those conditions we're going to prove that we can factor the polynomial into a product of linear and quadratic factors, each having real coefficients. So we start with our function here, and then from lesson 3 we had a number of identities for complex numbers, and basically what we need here is we want to show that the conjugate of f of z equals f of the conjugate of z. And the way you get that is the conjugate of a sum is the sum of the conjugates. We proved that earlier. And then the conjugate of a product is the product of the individual conjugates. That gives us these terms in here. And since a1, a2 up to an are real, when you take the conjugate of these, you just get the same thing. So the conjugate of a function is the function of the conjugate. And if f of z sub 0 equals 0, then f of the conjugate of z sub 0 equals the conjugate of f of z sub 0, which equals the conjugate of 0, which equals 0. And the implication here is that complex roots come in pairs. So if z sub 0 is a complex root, then also its conjugate. We'll need that to prove the theorem, which we'll get to in the next slide. Continuing with the proof from the previous slide, we first note from the fundamental theorem of algebra that we can write f of z is the product of linear terms here, where the z1, z2, z sub n are roots. Some of them may be complex. And in fact, if z sub I and z sub j are complex conjugates, in other words, z sub j equals the conjugate of z sub I, and they're also roots of the of our function, our polynomial, then we can replace z minus z sub I times z minus z sub j by just putting in the conjugate here of z sub I. This comes from the fact that we know that conjugates come in pairs. And then you multiply this out and you get z times z, that gives you z squared. And then you have minus zi times z, and then minus the conjugate of zi times z, that's this term here. And then you have zi minus zi times minus the conjugate of zi, that's this term. And when you multiply a complex number times its conjugate, it's equal to the modulus of that complex number squared. And when you add a complex number to its conjugate, you get twice the real part. That's this here. So that's pretty much what we wanted to prove, right? If we have any complex roots, we can write it, we can bring them together, multiply them, and then we get this quadratic. So 1 here times z squared minus 2, the real part of zi, is again a real number, and then the modulus of zi squared is a real number. So for all the complex roots, we can pair them together and get quadratic factors from our original polynomial. Then what's left are just the linear factors, z minus whatever the complex root is. So that's pretty much the proof of the theorem. Okay, let's do an example of the theorem we just proved. Let's take the function f of z equals e to the 7th minus 1. Its roots are given by the formula we derived in lesson 4. They're known as the roots of unity. I put the equation down here just to remind you. When you put in m equals 0, you get 1, although you can see that right off that 1 is a root. Then the other roots comes from putting n equals 7 and then m equals 1 to 6. So you put in 1, you get 2 pi over 7 plus I sine 2 pi over 7. If you put in 6 for m, you get 12 pi over 7. Then the cos, but that's the same as minus 2 pi over 7. So when you put in minus 2 pi over 7 for cosine, you get the cosine of 2 pi over 7 again. But when you put in minus 2 pi over 7 for the sign of the minus is minus the sign of that number. So you get a minus. That's why I have plus or minus here. And the same thing happens if you put in 2, you get, for m, you get 4 pi over 7. And when you put in 5 for m, you get 10 pi over 7, which is the same as minus 4 pi. And then when you put in m equals 3, you get 6 pi over 7. But when you put in 4, you get 8 pi over 7, which is the same as minus 6 pi over 7. So that's how you get these 6 additional solutions to z equals 1. And then we just use the formula from the previous slide. So you have z minus 1, our linear term, then you get z squared minus 2 times the real part of each one of these roots consecutively here. So it's the real part of this plus 1, then the real part of this one, and the real part of that one. So this is just plugging into the formula. And that gives us our factorization in terms of linear and quadratic terms with real coefficients. And I actually checked this out. I went to, I think it was Gemini AI, and I put that in there, and it multiplied it out, and it got z to the 7th minus 1. So you might want to play around with some of the AI tools or Wolfram Alpha to see if you can verify the solution. It's pretty easy. If you wanted to try other examples, I mean, you could take this one, z, you can just make it a 9, z, or even a simpler one, z to the 5th minus 1, or if you want to make it interesting, do z to the 5th minus 3, or you can multiply it times z minus 4. If you want to, so it's pretty easy to make additional examples if you're interested in testing it out on yourself. Okay, on this slide we're going to do something called the Taylor series for a polynomial. You may recall from calculus we had a Taylor series for things like sine x and e to the x, and they were infinite series. In this case, when you're working with a polynomial, you're just going to get a finite series. If you want the polynomial about 0, then for this particular example, z cubed minus z squared minus 4z plus 9, you already have it about z equals 0. But if you want to do the Taylor series about z equals 1, then you need to rewrite this function in this format here, where you have z minus 1 squared, and z minus 1 cubed. And the problem is to find the values for the coefficients here. One way to do it is to expand all that out and equate the constant term you get on here was 9, and then the linear terms from these three, and equate that to minus 4. Then you take the coefficients of the square terms here and equate that with minus 1. And then, well, the last one is just, there's only one z cubed, so a3 has to equal 1. So basically you have equations in 3 variables, 3 equations, 3 variables, and you need to solve that. That's one way of doing it. Another way of doing it is what I'm going to use here. You put in a 1 in both here, this equation and this equation here. And when you put it in here, of course, these 3 cancel and you just get a0. When you put it 1 here, you get 1 minus 5 plus 9, that gives you 5. So a0 equals 5. If you take the derivative of both of these and plug in 1, here you're going to get, you notice this, the derivative of this a0 is 0, and the derivative of each of these still has a z minus 1 in it. So you're just left with a1 here. When you take the derivative and then evaluate it at 1, you get a1. So that's the trick. And then you take the derivative of this, which I didn't write out, but it's minus 3 when you plug in 1. I mean, you know what it is from our previous work. It's just 3z squared minus 2z minus 4, and you put in 1 and you get minus 3. And you get the other the other two coefficients the same way. You just take derivatives and you start eliminating terms. So when you take the second derivative, both this term and this term vanish. And you're going to get here 2 times a2. And this will still have a z minus 1 left. So when you put in the second derivative evaluated at 1, you get 2. I wrote it as 2 factorial, but it's just 2 times a sub 2. You take the second derivative here, you plug in 1, and you get 4, and then you solve for a2, and you get 2. So if you had like a higher degree equation, you just keep taking derivatives, you eliminate terms, and you kind of build up a factorial here. You would have 3 factorial by the time you've taken the third derivative here. And you plug 1 into that, and you get 3 factorial a3. And you take the derivative 3 times here, and these 3 terms go to 0, but this term just is 6 or 3 factorial, and so you solve for 8. We already knew a3 was 1, but so that's the technique. And I believe I just wrote it out on the next slide. I wrote it out here. You just put in these values, and you get the Taylor series about z equals 1 for this function here. Okay, so just summarizing from the previous slide, we found the Taylor series about z equals 1 for a cubic complex polynomial, and was this equation here. So if we had a higher degree polynomial to start with, I don't know, z to the 5th, then you just need to take more derivatives and use the same methodology that we've employed to get this solution here. And I've written it out in general format here. It looks rather menacing, but you just have the point around which you want to find the Taylor series is in each one of these terms. And to find the coefficients, you need to take progressively more derivatives and evaluate it z sub 0, and then divide by n factorial. And you only get a finite number of terms. So if this would be the for an nth degree polynomial. We can take a rational function, as we defined earlier, and break it into what are called partial fractions. You probably remember this from calculus. I hope you do, because that's the technique we're going to use here. Let's start with an example. We have f of z equals this quotient. I've already factored the denominator because that's what we need to do in order to break this into partial fractions, which in turn are used to find integrals. This is why we're looking at this here. So f of z can be written like this. You need to have, if whatever the power is here, you need to have multiple terms in descending powers. And of course, z plus 5 is just to the power 1, so we only have one term for that. And the trick is to find these 4 coefficients. So one approach is to add these back together, get a common denominator, and then multiply everything out in the denominator. You get a fairly long expression, and then you equate coefficients with this denominator and the denominator here, and you get several equations which you need to solve simultaneously. And if you do that, you'll get this solution here. So it's not an easy one to solve. I cheated, to be honest. I went to Wolfram Alpha and I put in this function here using this notation, and I asked it to represent it in partial fractions, and I got this answer here. Okay, so we're going to do it another way in the following slides, but one way, as I say, is to use systems of equations, and there are some tools to find the solution for you in that case. Okay, on this slide and the next, we're going to show another way of finding the coefficients for the partial fraction. of this function here, f of z. I'll just write it down here again so you can remember what we're working on. And we want to find these coefficients here that let this expression equal that. So to find a, what we do is we multiply by z plus 5 times both this equation and this form of the expression. And then we take the limit of z equals minus 5. So you can see going to the right here, we took z plus 5 times this. The z plus 5's cancel. You take the limit, you plug in minus 5 for z. You get 25 minus 20 minus 3 over minus 8 cubed. And you get 1 over 256. And then if you do the same to this, you multiply it times by z plus 5. This first term is just a. And these other terms all have a z plus 5 in the denominator. So when you take the limit as z approaches minus 5, these all go to 0. And you're just left with a, which is what I've written here. To get b3, we multiply by z minus 3 cubed. First times this function. See that here, the z minus 3 cubed cancels, you get this, plug in z equals 3, get 8 in the denominator, 9 plus 12 minus 3 in the denominator, and you get 9 over 4. If you multiply z minus 3 cubed times this, all of these, this term becomes b3. This first term has a z minus 3 cubed in the denominator. This has a z minus 3 in the denominator, and this has a z minus 3 squared in the denominator. So when you take the limit as z approaches 3, this term, and this term all cancel to 0, and you just left with b3. Okay, continuing with the problem, we want to find the coefficient b2 in this case. So let's multiply this expression here by z minus 3 cubed. And when you do that, we get these terms here. We still want to take the, we're still going to need to take a derivative here because we want to isolate this b2 term. So you notice if we didn't take a derivative, we would be back where we were when we found b3. But if we take a derivative, then this term here still has a z minus 3 in it. So when you evaluate it at 3, this drops off to 0. The derivative of this term is just b2, which is what we're looking for. The derivative of this term is 0, so that goes away. And then when you have it cubed here and you take a derivative, you can look at this as the product of a z minus 3 cubed times 1 over z plus 5. So both of the terms in the derivative, if you use the product rule, is going to have at least a z minus 3 squared in it. When you take the limit, this term will go to 0. And so when you, just breaking it into pieces here, and when this term goes to 0, this goes to 0 as I mentioned above, and then they're left with b2. So that's half of the problem. The other half is multiplying f of z by, let me show that here, f of z times by z minus 3 cubed. So we're working on this here. And then the z minus 3 cubed cancels this, and you have the derivative of this quotient here. It's kind of long. It's used the quotient rule. You notice you have the bottom squared, and then it's the derivative of the denominator times the bottom minus the denominator times the derivative of the bottom, and you collect the terms together. And you get this, then you plug in z equals 3, and you get 31 over 32. So b2 equals 31 over 32 using this procedure that we've been working on here. We still have b1, and it turns out we're going to need to take 2 derivatives to isolate b1, which we'll do in the next slide. Okay, we're almost there. So as I mentioned the last time, in the last slide, we're going to need to take two derivatives to isolate b1. So we do that, and we take two derivatives. First we multiply by z minus 3 cubed, and then you take the derivative twice, and you're left with this first term here. You need to take the second derivative of that, and I kind of left out the details here, but when you take two derivatives of this multiplied by z minus z cubed, this one is you're just going to get 0. This one you're going to get b2 times z minus 3. When you take the derivative twice, you get 0. And then this last term you're going to get b1 times z minus z minus 3 squared, and you take the derivative of that twice, and you get 2b1. And this expression here, when you take the derivative twice, all the factors that remain have a z minus 3 in it. So when you take the limit as z goes to 3, you get 0 for this. And we need to do the same thing to this expression here. Z minus 3 cubed times f of z. The z minus 3 cubed cancels. Excuse me. And then you have to take the second derivative of this. It takes a little bit of work, but it does simplify to a fairly easy expression to plug in z equals 3. You get 4 over 8 to the third power, and so we're left with 2b1 equals 1 over 28, or b1 equals 1 divided by 256. So I left out a few steps in here, and you can see if you had a say a z minus 3 to the fourth, and you would have to take 3 derivatives to isolate that final factor. I mean, you would have 5 factors now, and to get that last factor you would have to do 3. So it gets more involved. Even this relatively simple example, you need to do quite a bit of work. On this slide, we summarize the general procedure that we employed on the last several slides concerning our example. We have a rational function f of z equals p of z over q of z. The first step is to factor q of z in terms of its roots. The second step is just to write down the partial fraction representation. So for the first one here, for the first root z sub 1, we need a coefficient over z minus z sub 1 to the n1 power, and then to the n sub 1 minus 1 power, all the way down to the power of 1. And you need to do that for each one of the roots, so you get this rather lengthy expression here in general. And as we discussed previously, there's two approaches. One, we can add these all together and solve simultaneous equations, and the other one is this approach that we used with limits and derivatives, which I'll explain in the next slide, or at least summarize in the next slide. In summary, we have two methods for finding the coefficients of the partial fractions. The first method is to add up the partial fractions, get a denominator, equate the coefficients of that denominator with the function p of z, which was the denominator of the original rational function, and then we have a system of equations, linear equations, to solve. That was one approach. And the other approach was using limits and derivatives to isolate the different coefficients and then solve the problem that way. So a couple of caveats. I wrote the formula here in general format, which is a bit hard. You may want to write this down and go back to our example and see how it fits with the example. This is more general, of course. I equals 0 means you don't take a derivative here. And then all the other values of I, it's first derivative, second derivative, and so on. And the other point I wanted to make is an advantage of this approach is you can find any one of the coefficients independent of finding the other ones, unlike this approach, the first approach here, where you have to solve the system of equations and get all the coefficients. So if you only needed one of the coefficient or a few of them, you could go to get them directly using this formula and not having to solve for them all. Okay, so that's it for this lecture. The next lecture is going to be on trigonometric functions, hyperbolic, trigonometric functions, and the exponential function.